doing some more BCA charts. Just a reminder, like I said, this BCA charts is a problem-solving strategy. It is not intended to be easier or harder or anything like that. But what it does is it gives you a complete understanding of what's going on in a chemical reaction. And when we get to a little bit harder problems, I find that kids, if they don't want to use the BCA charts, just can't do these problems. So what happens is when we get to limiting reactants, there's a certain part of the problem it's impossible to do if you don't use BCA charts. So when I run into AP chemistry, like when I'm trying to teach stoichiometry to kids and they didn't learn how to do BCA charts, they kind of dig their heels in and they're like, I don't want to use that. But then it keeps coming up over and over and over again because it is a really important problem-solving strategy that a lot of times you can't do problems without. I use this equation a lot because it's got coefficients in it, but it's still nice and easy. And also, you guys are super familiar with aluminum and oxygen. And whether you knew it or not, you're also super familiar with aluminum oxide. The reason I say you're familiar with aluminum oxide is because anytime you see something aluminum, for example, airplanes are usually made of aluminum. There's a coating of aluminum oxide on the outside because most metals typically are very reactive. And so is oxygen. So there's always a coating of aluminum oxide on the outside, and that protects it from corroding. So aluminum is an amazing metal, but he loves oxygen. So for a long time, they thought that aluminum was a super rare metal. They actually used to make like crowns out of it and stuff because they thought it was so rare that it was amazingly expensive because they couldn't find it. They couldn't get it away from oxygen. Could not talk it away from oxygen. It wasn't really until this past century in the 1900s where they found a way to get it away from oxygen. So it's a fairly recent discovery. And you might think to yourself, yeah, I don't care about that. Except for the fact that aluminum is so light. Look at the molar mass of it compared to a lot of other metals. Aluminum is so light and fairly unreactive compared to the alkali metals and the alkali earth metals that we make airplanes out of it. If we had to make airplanes out of another metal that was not super reactive like iron, it would be so heavy and jet fuel, it would take so much jet fuel, you'd only be able to take short plane rides and only the super rich would be able to afford it. So us getting aluminum away from oxygen is a super important scientific discovery. It allowed us to develop airplanes, which I don't know about you. I love to travel. I don't love to fly, but it gets me from point A to point B, so I'm super grateful for that. So remember, the first step on any problem is to balance the equation. So I noticed that there's 3 oxygens on the product side and 2 oxygens on the reactant side. Remember, my strategy is always to double the odd. And I'm going to balance that by inspection. So I'm just going to make up a problem. Let's say we have let's do a nice round number, 100.0 grams of aluminum. How much aluminum oxide will I produce? There's only one product here, so if I say how many grams of product, I know I'm talking about aluminum oxide. So I'm going to do a BCA chart. Remember, B stands for before, C stands for change, A stands for after. In BCA charts, we always use moles. So I'll rewrite this down here so we don't get confused. So we're going to make columns for each of the reactants and the products. So remember, in order to use a BCA chart, we have to have moles. So we're given grams in this situation. Now, you don't have to keep doing these conversions on paper. Once you get good at this, you'll recognize that if I want to change grams to moles, I divide by the molar mass. So the grams to moles conversion is done by dividing. So 100 divided by 26.98 will give me moles, and I'm going to put this in the BCA chart. 3.706. I carry around lots of significant figures just to make sure. Now, if I react all of the aluminum, that means that I have plenty of oxygen. So I just use the term excess because I don't need to concern myself with oxygen. Before a reaction even starts, we have no products, so we have a 0 for the products. Remember, that's before the chemical reaction starts. Now, each of the reactants gets a negative sign because the concentration of the reactants is always going to go down as we produce products. The products will get a plus, like such. Then we bring down the coefficients. So this number right here gets brought down on each one of these columns. So this is going to be 4x, 3x, and 2x. So this is actually a problem. And afterwards, all of the aluminum is going to get used up. I'll still have leftover oxygen because I had plenty of it. And we need to figure out what the value of X is to solve this. So this is right here what I'm going to use to solve for X. So my problem becomes 3.7064 minus 4x equals 0. Now we're going to solve this like we do any algebra problem. So I'm going to add 4x to both sides. Like such. So 3.7064 is equal to 4x. Now I divide each side by 4. And I get an answer of, for the value of x, is 0.9266. So now I can replace this x with the actual value of x, which is 0.9266. And that gives me the number of moles of aluminum oxide, which is 1.8532 moles of aluminum oxide is produced. Now, if I want to go from and switch this to grams, which I do, that's what it asked us to find. To go from moles to grams, you multiply. So when you're doing these problems, maybe it's good for the first several problems that you do to put this next to your problem or top at your assignment so you can always look. So I'm going to take, and I'm going to show you why I multiply, because I'm going to take 1.8532 moles of aluminum oxide. This is the actual problem. And I'm going to multiply by the molar mass to change from moles to grams. And let's see, I'm going to calculate the molar mass. 26.98 times 2 plus 16.00 times 3 gives me 101.96. Now, in my calculator, I just put the multiplied sign in because I already have the number written there, and I get an answer of 188.9523 grams, and I'm going to round it to the right number of sig figs, which comes from my given. So let's look at this given, 100.0. So it has a non-zero digit that is significant, and then it has 3 trailing zeros. So you ask yourself, is there a decimal? Yes, there is. So that's 4 significant figures. So I'm going to round this guy up, which makes it 189.0 grams of aluminum oxide would be my reported answer.